Good morning. My name is Raili Virtanen and I am here to present my master's thesis titled Explainable AI Techniques in Trustworthy Object Detection. This thesis was done in collaboration with TietoEVRY and Aalto University. Here is the agenda for this presentation. First, I will introduce the problem and give some background information about it. Then I will talk about Trustworthy AI, what it is, and how it is defined in this thesis. I will further discuss Explainable AI, which is one of the principles of the Trustworthy AI, and introduce some explainability techniques. Then I will show the experiments and results done in this thesis and conclude this presentation. As mentioned before, this master's thesis was done in collaboration with TietoEVRY, so the assignment came from there. This work was done for an EU project called 5G Timber, which aims to support the uptake of 5G technologies in EU timber industry. The use case that this thesis is connected to is called Precise Localization for Production Processes, Optimization and Human Safety in a modular woodhouse factory, which aims to improve human safety and to have precise localization methods for safer indoor logistics using 5G technologies. An object detection model was designed and developed by Suha Chowdhury for this use case and for her own master's thesis titled Computer Vision Assisted Safety Alert System for Industrial Settings in Private 5G Networks. The model is designed to detect objects in a warehouse and send out real-time alerts when, for example, a worker and a machine are about to collide. The object detection model is an AI system that was developed using YOLO model, which is a real-time object detection algorithm. My thesis evaluates the trustworthiness of the object detection model in the context of warehouse safety using some explainability techniques. As mentioned, the use case aims to improve human safety and to have precise localization methods for safer indoor logistics in a modular woodhouse factory. All the data used in this master's thesis comes from the project 5G Timber, but due to confidentiality and privacy reasons, I cannot show real images from the project. However, the picture on this slide is an example of a modular woodhouse factory that is very similar to the data used. There are multiple people and machinery moving around themselves and moving other objects, so accidents do happen sometimes, so it is crucial that the workplace is safe for all the workers and accidents can be avoided. A modular woodhouse factory is essentially a big warehouse with people and different smaller and bigger objects. So the research objective in this thesis is to assess an object detection model developed for safety in a warehouse setting from the perspectives of Trustworthy AI and explainability as a third-party auditor. The first object is to assess the model's ability to detect objects, which means that the thesis goes through 20 different warehouse videos and see how many objects the model detects and with what confidence. Also, how the model performs when the objects are partially or fully occluded will be looked at. This analyzes whether the object detection model is trustworthy. Explainability evaluation will happen with two different experimentations. First, experimentation will use parameter tuning with one video where input parameters will be changed with the aim of improving model accuracy and explaining the model's behavior. Second explainability experimentation will be an attack on the object detection model by using synthetic patches to occlude objects. This will be done on different videos, and each individual object that the model was trained with will be experimented on with synthetic patches. The object detection model has been trained with class labels machine, crane, tow tractor, and waka, and the aim is to see whether it can be explained what parts of the objects have effect on the model's behavior. Artificial intelligence and AI systems have become more talked about and known by the public. Whether it is a self-driving car or a chatbot, artificial intelligence is all around us. So how can people make sure that the AI systems are safe and trustworthy to use, and what does it mean? Trustworthy AI includes many aspects and stages of the life cycle of an AI system, and there have been developed several guidelines and frameworks to define it. Their aim is to prevent harmful use of AI and make all the stakeholders more aware of the possible risks. This thesis goes through 4 documents on AI guidelines and frameworks, and uses their combination to define the meaning of trustworthy AI. The documents are EU AI Act, USA's Executive Order 13960, AI Recommendations by OECD, and AI Risk Management Framework by National Institute of Standards and Technology. All of these documents have defined trustworthy AI through similar principles that need to be met for an AI system to be trustworthy. Here are the principles defined by the different documents. The principles are grouped together by their similarities, even though some word choices may be different. The principles are grouped by their meaning, and one can see that every document has a mention of almost each principle. Next, I will go through each row and explain briefly what that principle means and what does it mean for an object detection model. Technical robustness refers to the ability of AI systems to operate effectively under different circumstances, including uses that were not initially anticipated. There need to be resilience against errors, noise, and unexpected inputs. So an object detection model should not be affected by noise on the video or if some pixels are broken on a camera. Transparency reflects to which extent the inputs and outputs of an AI system are available to stakeholders using it. It includes all the data sets and the processes that affect AI systems' decision-making. People should also know how to operate the system and have control over it. So everyone who is affected by the object detection model should have the knowledge about its existence and the way it operates. Accountability means that AI actors should be accountable for the right functioning of AI systems, which includes ensuring responsibility for AI systems and their outcomes before and after their development, deployment, and use. In the case of an object detection model, every actor who participates in designing, developing, deploying, and using the object detection model should be held accountable for the model to work correctly. Safety means that AI systems should not pose unreasonable safety risks to human life, health, property, or the environment. And safety should be considered throughout the system's life cycle. The object detection model should be safe for all the people working at the factory. Since the model's function is to improve safety, it cannot make the warehouse environment more dangerous. It should be able to detect objects and give eventually alerts when 2 objects are dangerously close. Fairness and managed bias refers to the idea that AI systems should be designed, developed, acquired, and used in a manner that respects human rights, civil liberties, democratic values, and rule of law. But also, it includes enabling inclusion and diversity by ensuring equal access to AI systems and equal treatment while using them. So for an object detection model, every person working at the warehouse should be treated the same and not distinguished by anything by the model. Any visual differences in people's appearances should not affect the outcome of the model. Explainability means that AI actors should make sure that all the stakeholders have sufficient understanding of functionalities and outcome of AI systems. Decisions made by AI systems should be traceable and understood by human beings, and especially when those decisions have significant impact on people's lives. In the object detection model's case, the actors around it should be able to explain how it works and why does it give certain outcome. The end result of the model should not be a surprise to anyone. AI systems should be secure and resilient, which means that they need to be protected against vulnerabilities that can allow them to be exploited by adversaries. Attacks may target the data, the model, intellectual properties, system uses, or infrastructure concerning the software or the hardware. The object detection model should be secure and not vulnerable to adversarial attacks. The model should be secure so that it could not be exploited or make it miss dangerous situations. Privacy refers to a fundamental right that everyone should have, which refers to norms and practices that protect human autonomy, identity, and dignity. Anonymity and confidentiality should guide AI systems design, development, and deployment. Since there are people working at the warehouse, their privacy needs to be protected. The object detection model cannot violate their privacy or collect any personal data about them nor use it. Societal and environmental well-being means that AI systems should always be in pursuit of beneficial outcomes for people and the planet. The object detection model should be more efficient and environment-friendly in the long run, since it should reduce the number of accidents or potential accidents. Previously spent time and resources on accidents could be allocated better in the future. So the trustworthy AI is designed through these principles, and it is important that they are met throughout AI systems' whole life cycle, meaning that during the design and development processes, the principles should be met, but also when the product is used by consumers for an AI system to be trustworthy. As mentioned before, explainability is one principle of the trustworthy AI, and it answers to how an AI system is working and why it reaches specific outcome. Explainability in AI is important because people developing and using the system need to understand how it works and why it comes to specific conclusions. It is especially important when there are safety-related questions. An AI system cannot make a situation unsafe, and in a case when it does not work as expected and causes a risky situation, it is crucial to know what went wrong. Complex machine learning models are often referred to as black boxes, whose inner processes are unclear to humans. Explainable AI is the field that focuses on the techniques and methods to understand how these black boxes work and aim to make them into understandable machines. YOLO algorithm that was used for the object detection model utilizes deep learning networks, which makes it hard to understand, and one can call it also a black box model. There are several techniques that are popular when analyzing the explainability in object detection. Perturbation-based methods modify systematically different parts of the input image and analyze the output. That way it can be compared which parts of the input image are more important to the output. Perturbation-based methods can include, for example, occlusion, blurring, or masking, and they can be applied to any deep learning model regardless of its architecture or the way the model works. On the right is an example of a masked picture of men. Saliency-based explainability methods highlight important parts of images that contribute to the decision made by deep learning networks. Each pixel of the input image is assigned an importance score according to how much it contributed to the prediction, and that provides the saliency map. Saliency map is essentially a heat map where different pixels show their importance, usually through color, on the detected object. On the right is an example of a saliency map highlighting a tennis racket. Adversarial patch attacks are perturbation-based methods to influence AI systems' decision-making. Real data samples are modified by an attacker by adding visual patches. Studies have shown that adversarial patches can also target object detection models, and since object detection models work on real-world tasks, the attacks can successfully also work in that environment. Research is focused on the countermeasures of the adversarial attacks, since the countermeasures help to understand how the attack works and can identify the vulnerable area of the object detection model. adversaries working against object detection model with adversarial patches can have a specific goal. For example, to prevent the object detection model from detecting a specific object, or to let the object detection model detect an object but classify it incorrectly, or to make the object detection model detect an object that is not really there. These adversarial patches can be used in studying the explainability of the object detection model and make it more understandable. As mentioned before, this thesis includes 3 experiments. First is called model assessment, where the experimentation looks at the way the object detection model works with 20 different videos. What it sees, how it labels the objects, and with what confidence. Also, it is looked at whether an object is partially or fully occluded and how that affects the model. The results are divided into 3 different tables. Normal detections show detections of objects that are fully or nearly fully visible. Partially occluded detections show detections where the objects are partially occluded. And last table is called other detections, that include detections that are relevant but do not fit into any other table. Second experiment is called parameter tuning, where one video is chosen based on the object detection model's insufficient performance. Some of the model's parameters are changed, and then the result is compared with the detections done with default parameter values. Third experimentation is an occlusion attack using synthetic patches. First, each different object that the model was trained for is occluded by different synthetic patches to see whether some part clearly affects the detection. Second part is placing synthetic patches randomly in one video with a lot of movement to see their effect on the end result. As said before, the class labels that the object detection model was trained with are machine, crane, tow tractor, and worker. Here is an example of results for one video where it has 2 people walking around and working. Person 1 is constantly in the frame and sometimes partially occluded. They are detected all the time. Person 2 goes in and out of the frame and they are partially occluded at all times. There is also one still forklift in the background that the model detects occasionally, and on the right side of the frame there is a pile of metal rods that the model is misclassifying as a machine sometimes. So the first table shows detections where the objects were fully visible. The second table shows detections where the objects were partially occluded, and the third table shows a detection with wrong classification. All the 20 videos are gone through in the same manner, and the results are shown in a similar tables. In these 20 videos, there were in total 56 objects to detect that would fit the classifications the object detection model was trained with. The model detected in total 16 machines, 35 workers, 3 tow tractors, and 1 crane. In total, 55 objects. Only in one video the model did not detect a forklift that was partially visible but not far away from the camera. So all in all, it can be said that the model detects the objects it was trained for very well. However, there were a total of 14 objects that were something else, but the object detection model still detected them. For example, some red or orange objects were labeled as workers or tow tractors. It can be seen from the video that many of the workers wear orange shirts and all the tow tractors are also orange, so the object detection model was probably trained with these type of images. The same happens with dark objects that are something else. The object detection model labels them as machines, and this is probably because machines used for training had dark coloring in them. The model is quite confident in its detections when objects are fully visible, since the difference between the lowest and the highest confidence score for an object is under 0.5 for almost every fully visible object. This shows consistency in model's behavior. The object detection model has detected well partially occluded objects. In the cases where an object was detected without occlusion and with occlusion, there is a difference in the confidence scores. Most of the time, the detection without occlusion has a higher confidence score, but the model still performs well with correct labeling. In the context of warehouse safety, it is important that the object detection model is confident in its labeling, so that accidents can be avoided. For a model to be trustworthy in a warehouse environment, it needs to detect all the moving objects and label them correctly with good confidence, so that the model can give out real alerts. Wrong labeling can result in either wrong positive alerts or missing real events requiring an alert. This object detection model has performed well and improves the safety in a warehouse setting, so it can be considered trustworthy. Parameter tuning was an experimentation done with a video where a forklift carrying a warehouse top enters from the top of the frame. The forklift is sideways and partially visible at first before it turns and starts moving toward the bottom right corner of the frame. At this point, the warehouse top hides part of the forklift and the model does not detect it. While the forklift moves along the path, it is fully visible and not detected by the model. In the end, the forklift begins to leave the frame and the model only detects it when the warehouse top is out of the frame. These detections are in the table on the left. The table on the right shows the detections after some parameters have been modified. Usually the parameter tuning happens during the training of the model, so there are more options. In this case, training was not possible, so the focus was on the parameters that are used in prediction process, such as parameter image size. The model performs better when the image size is reduced, and it recognizes the forklift when it is fully visible when it previously wasn't. Synthetic occlusion attack is about experimenting with different objects that the model is trained with and see how differently placed patches affect the end result. The patch sizes and positions depend on the part that need to be occluded. In this thesis, all the patches had rectangular shape. This table shows the results with experimenting on a tow tractor. Most of the patches result into smaller confidence values, and some result into the model not detecting the object. With other trained class labels, the results are similar with smaller confidence values or the model not being able to detect. There were not any individual areas of an object that were occluded that would result into the model not detecting it, except for the orange part in the tow tractor. The size of the patch also affected the end result. The bigger the patch, the lower the confidence score. Second part of the synthetic occlusion attack was experimenting with random patches on one video to see whether randomly placed patches have a significant effect on the end result. 10 patches were placed randomly on a video with a lot of movement, and in half of the cases, the patches did not have any effect since their places were not crucial for the object detection model. But in other half of the cases, the patches occluded workers at least partially, and it affected the end result. This shows that random attacks could affect the model's ability to make a detection and compromise its trustworthiness, especially in cases where there are a lot of movement and possible accidents need to be avoided. So in conclusion, the experimentations have shown that the object detection model is mostly trustworthy since it was able to detect and correctly label many of the objects. The model detected 55 out of 56 different objects, at least at some point. However, there were also detections with incorrect labeling that the model made. These type of detections could possibly cause false positive alerts. The object detection model performed well with fully visible objects and partially occluded objects as they were mostly detected and labeled correctly. Most of the time, the confidence of the model was smaller with partially occluded objects than with fully visible objects, which is probably because of fewer visible characteristics that the model bases its detection on. Parameter tuning and synthetic patch attacks were used as a method to increase models' explainability. In parameter tuning, it was found out that when model's parameter image size is changed, it can increase the model's ability to detect an object at moments when it was previously undetectable. Patch attacks concentrated on finding out whether some characteristics were crucial for the model in making a detection. It was found out that there were no such characteristics, except for the tow truck's orange color. The object detection model bases its detection on multiple parts of the object, so occluding some part does not make the model fail. Only occluding tow truck's color made the model not detect it. The object detection model is mostly trustworthy, and it can increase safety in a warehouse since it detects and labels objects correctly. Also, occlusions are not a big issue for the model unless the object is almost completely occluded, because it detects well partially occluded objects, which increases its trustworthiness. The object detection model could be developed further in the future to make it more trustworthy and decrease the number of possible false positive alerts by training the model with more objects relevant to the warehouse. Thank you for listening and have a nice day. Thank you.